Can everyone see the slides? Yes. Okay. So the first question that I have told you to attempt was question 10.10. Okay. So 10.10 says consider the four bus system depicted in figure 716 of LGAT, which is this figure. Okay. The line data given were given in problem 7.9. So problem 7.9 says that all three lines are identical and each can be represented by a series of 7 plus J35 ohms per phase. Okay. The generator is rated 500 MVA and has a transient reactance of 0.25 per unit based on its own rating. The transformer has equal megavolt ampere ratings. Its reactance is 12%. Find the short circuit capacity of each bus, assuming all prefault voltages to be 1 per unit. Okay, don't worry, your friends who are not here, this is being recorded. So, the equivalent circuit is given like this. We have a generator or transformer, bus 1, line 1, bus 2, we have a load, line 2, bus 3, load, line 3, and bus 4 with a load. Now, how are we going to solve this? The solution to this problem is neglecting the line resistance, the line impedance equals J35 ohms. Okay, so here we are going to neglect the line resistance, which is 7. So we are only going to consider J35. Okay, everyone is typing. What is the problem? Can't can you record this? Yes, this is being recorded. Don't worry, this will be recorded and I'll put it on YouTube. So don't worry. Okay, let's move on. So we're going to neglect the resistance. So we are only going to consider J35 ohms using the 500 MVA base and remembering that the line voltages was 230 kilovolts. The line reactance equals to 35 divided by 230 squared divided by 500. Okay, remember this formula. So this will equal to 0.331 per unit ohms. So what will be our equivalent circuit? The line equivalent circuit is now drawn. We have our ground generator 0.370. Where do we get this from? We get this from the reactance, okay, transient reactance of 0.25 of the generator plus the reactance of the transformer, which is 12%, is equal to 0.12. So 0.25 plus 0.12 is equals to 0.370. Then we have bus 1, line per unit impedance is 0.331. Bus 2, line per unit impedance is 0.331. Bus 3, line again is similar 0.331. And then we have bus 4. So for solid short circuits at bus 1, 2, 3 and 4, we compute directly the SCCs. So SCC 1 will be equals to, remember the formula to find SCC, 1 divided by XT, the Thevenin reactance. Okay, the Thevenin reactance is 1. So here at first we have 1 divided by 0.37. So SCC is equals to 2.70 per unit MVA. Similarly, SCC2 will be equals to 1 divided by, okay, we are going from this side. So 0.37 plus 0.331, okay, which will be equals to 1.43 per unit MVA. Now SC3, again going from this side, so we have 0.370 plus 0.331 plus again 0.331. That's why we have here 1 divided by 0.37 plus 2 times 0.331 is equals to 0.97 per unit MVA. And then finally SEC4 is equals to 1 divided by 0.37 plus 3 times 0.331 is equal to 0.73 per unit MVA. Yes, Amit, this session is being recorded. Okay, don't worry. So this is how you compute your short circuit capacity. Is it clear? Was it hard? That's all you have to do. That's the solution. Anyone has any questions? Hello. Okay, no questions. Then we'll move on. So I hope everything was clear. I hope you will be able to do these types of questions. I don't know where. Okay, let's move on. Now 10.11. A 4 bus system has a total of 6 lines which provide interconnections between each bus and all the other 3 buses. All lines have same impedance J 0.1 per unit. There are equal generators and step-up transformers at each bus. The combined impedance, transient reactance plus leakage reactance of each generator a transformer is J 0.17 per unit. Find the SEC of each bus. All preferred voltages are 1 per unit. Yes, others. No, you don't have a question. Okay. So, what is going to be the solution for 10.11? Because of the symmetry, all 4 buses have identical SECs. Okay. Because it is symmetrical, we are going to say that all the bus will all the buses will have identical SCCs. We concentrate therefore on finding the SCC of one bus and choose number 1. So if we find what is the short circuit capacity for bus 1, that will be the same for bus 2, 3 and 4. Okay. So as viewed from the Thevenin EMF ET, okay, we have our Thevenin EMF here. The rest of the network looks completely symmetrical, and the EMF will thus feed equal amounts of currents into lines L1. Okay, L1 is this, L2 and L3. The buses 2, 3 and 4 will therefore have identical voltages, meaning that we may connect these 3 buses into a joint node. Okay, as shown in step 1, we are going to see that shortly. Okay, so when you have a question like this, first thing that you have to do is make a system like this. So what did this question say? 4 bus system. So 1, 2, 3, 4. All right. There's total of 6 lines which provide interconnections. So first we are going to connect 1, okay, and then 2. If you want to say 2 here, 2, 3, 4, and then interconnections from here 1 and 2. So in total we have 1, 2, 3, 4, 5 and 6. Okay, and then we are going to put down our reactance that is given. So here for our generator and transformer is J 0.17. So we are going to write here 0 J 0.7 or 0.17, sorry, and our line reactance is 0.1. So all lines will have reactance of 0.1. Okay. Now what we are going to do? We are going to reduce this second. So first step, as we mentioned here, that we are going to only select bus one. Okay. So we are going to say this line one, line two, line three are all identical, and all are going to one bus. So we are going to put something like this. So step one, after reduction we have ET, okay, and then our reactance generator and transformer 0.17. Then we have lines 1, 2, 3, okay, all are each of 0.1, which are going to be connected to buses 2, 3, and 4. And these three buses are then connected to the generators. So we have generator 1, 2, 3. Generator transformer, remember, generator transformer is 0.7. So we have it like this. Any questions, anyone? No, is it clear till now? Clear? Okay. Now, step 2. What are we going to do? This inductance here we can add them in parallel. So adding this inductance in parallel, we get, okay, line inductance in parallel 0.1 in parallel with 0.1 in parallel with 0.1 will give you 0.0333. Okay, and this 3 in parallel will give you 0.0567. You can calculate and you will see you will get the same results. And we leave this as it is. Now we move to the next step. Next step, we are going to add the line reactance and the total line reactance plus the total delta transformer reactance in series. So 0.0333 plus 0.0567 in series is equals to 0.09. So we have this circuit here now. So we have our ET, our transformer and generator reactance, and our total. So again, what can we do here? We can add this reactance in parallel. So if we add 0.17 in parallel with 0.09, we get 0.0588. This is our equivalent Thevenin circuit. So what does the formula say? SCC will be equals to 1 divided by the Thevenin reactance, and our Thevenin reactance here is, okay, 0.05. Let me just correct this. This is 0. Okay, 0.01 divided by 0.0588, you will get 17 per unit MVA as your short circuit capacity. So you see, it's not that hard, right? You have this complex circuit. Okay, this is what something similar to what you are going to have is the grid. Okay, the network of your project, Cyclops Island. So if you are to find the SCC, okay, these are the steps that you are going to follow to come to a Thevenin reduced circuit to find your SCC at a particular bus that you require. For us, everything was symmetrical here. For your case, I don't think so. It will be symmetrical, but this is the procedure that you are going to use. Is that clear? I hope this gives you a little bit of idea. Okay, what you have to do. Yes. Also, this is important for your quiz, as I have mentioned earlier. Okay, and this quiz will be our last quiz. There is no quiz for chapter 12 because we are not covering chapter 12. Okay, the whole thing of chapter 12. So I'll stop this recording here.